Proof by contradiction. Pi is irrational. Proof by contradiction. Consider the following problem. Prove that the square root of 2 is irrational. Let's outline this proof. First, we will assume that the square root of 2 is rational. That is, we're going to let the square root of 2 equal a fraction, a ratio of integers. We'll also require that the greatest common divisor of the a and b is equal to 1, so that the ratio a over b is in simplest form. Now, based on this assumption, let's see what this implies. If the square root of 2 is the fraction a over b, then squaring both sides of this equation leaves us with 2 equals p squared over q squared. Therefore, 2q squared is equal to p squared. Another way to say this is that p squared is a multiple of 2, making it an even number. And if p squared is an even number, that implies p must be an even number. So p is an even number. Now if p is an even number, let's write it as a multiple of 2, that is 2 times an integer k. Substituting that back into our equation, we get 2q squared is equal to the quantity of 2k squared, or 2q squared equals 4k squared, which allows us to write q squared as a multiple of 2. So now if we have assumed that the square root of 2 is the ratio of 2 integers, then we've also shown that p, one of those integers, is an even number. And because q squared is equal to a multiple of 2, that means q, the other integer, is equal to an even number. Putting this all together, if the greatest common divisor of the two integers is equal to 1, and we've shown both of those integers are even numbers, we cannot have that happen at the same time. That's a contradiction. So because we've arrived at a contradiction, we can draw a conclusion. That implies that our assumption is false. Therefore, the square root of 2 is not the ratio of 2 integers. The square root of 2 is irrational. A quick fact: the square root of 2 is irrational, but it is also an algebraic number. Pi, however, is irrational, but not an algebraic number, and for that reason, it is called a transcendental number. But for now, we're going to focus on proving that pi is irrational. How to prove pi is irrational? This proof was given by Niven in the 1940s. This is a proof by contradiction, so we start out just as the square root of 2 proof did, by assuming the number that we're interested in here, pi, is a rational number. So mathematically, we're going to leave pi as the ratio of 2 integers a over b in simplest form. So this is our assumption. And through our proof, we will show that this assumption is false. Niven's proof starts by defining a function f of x as x to the nth power multiplied by a minus bx to the nth power over n factorial, where n is a positive integer. Now this function is constructed in such a way that its roots, that is, its zeros, are at x equals 0, as well as at x equals pi, which is equal to, in our assumption here, the ratio of a over b. The next part of the proof is to recall the binomial theorem. And we want to specifically focus on the binomial theorem for the binomial a minus bx raised to the nth power. The binomial theorem allows us to write this in a summation form of n choose k, a to the n minus k power times negative bx to the k power, summed from 0 to n. And the point about the binomial theorem here is that we want to observe the following: that since a and b are integers, that the coefficients of this expansion will also be integers. Recall that n choose k can be given by Pascal's triangle. Let's dive into this idea just a little bit further. So imagine f of x for a given n, let's call it f sub n, is equal to x to the n times a minus bx to the nth power over n factorial. And we'll choose a value for n, let's say n equals 3. So f sub 3 of x is going to be x cubed times a minus bx cubed over 3 factorial. Now we can go ahead and expand this out to see what it looks like. And we notice that its lowest power of x is x to the third, and its largest power of x is x to the sixth. So we'll focus on its lowest power of x. So we could typically write something like this, where we're looking at just its lowest power of x. And here we have the derivative with respect to that lowest power of x of f prime, and then we're going to write the remaining parts to that derivative as just stuff. And we can begin to see what the pattern is going to hold for that term with the lowest exponent of x. You see, by the time we take the third derivative of this, we get a constant a cubed plus some stuff, all in terms of x, which when we evaluate that particular function at x equals 0, we'll have a cubed be an integer, because a is an integer, and all the rest of that stuff will drop out to be 0. So the derivatives evaluated at 0 will always result in some kind of integer. And we can make the same argument for x equals pi, which we assume to be a over b. So if we look at the function that we were just talking about and expand it out with the emphasis on a minus b to the x binomial term, and consider the derivatives, but focusing on the powers of that binomial term, and really looking at the smallest exponent term like we did with the x, we can rewrite this first derivative as some stuff plus 3bx cubed a minus bx to the second power over 3 factorial, and then we can take the second derivative of that, and we're going to have some stuff plus, and you're going to see what we're going to do here is we're going to build a pattern for the term that has the smallest exponent. And here we're just writing it out. Once we get to the third derivative, we get again some cancellation to happen, and if we evaluate this at x equals pi, which is again a over b, we get something which is an integer. So the derivatives evaluated at pi, assumed to be a over b, will always result in an integer. So we're making the case for g of pi and g of 0 to both be integers when pi is equal to a over b. We'll define what g of x is in a moment. But we'll also recall something about the power rule for derivatives. This will play a role in this as well. If we take x to the nth power and find its derivative, it results in n times x to the n minus 1 power, and if n is a positive integer and x is an integer, then the derivative will also be an integer. Now we're going to establish a few properties here. These properties will be the heart of our proof. Now this will not be a very intuitive proof, so we'll have to work through the details here. We start off by showing that the integral from 0 to pi of f of x times the sine of x dx will always be an integer. We will next establish that this integral will be greater than 0 and less than pi to the n plus 1 power times a to the nth power over n factorial. Furthermore, we'll show that the limit as n goes to infinity of pi to the n plus 1 a to the n all over n factorial will tend towards 0. And to spell out what that really means, it means for n sufficiently large, that ratio will become a number in the interval from 0 to 1. In other words, it will become a proper fraction. Now, if our integral is nested between 0 and this ratio, and that ratio will tend to 0 as n goes to infinity, that'll suggest that this integral is not an integer. That is, that the integral is a proper fraction here, is in contradiction to our first property. You see, our first property established that that integral always was an integer. And now we've established that that integral for n sufficiently large would not be an integer. So properties 1, 2, and 3 cannot simultaneously be true. Therefore, our assumption that pi as a rational number, the ratio of two integers, is false, thus leading us to the conclusion that pi is irrational. Now, we must go through the work of establishing those properties to show those things hold true. So first, we have to show that the integral from 0 to pi of f of x sine of x dx is always an integer. This is sometimes referred to as an iceberg step because it is not obvious where this comes from, and you have to work through the details to get to it. So, the function that I mentioned earlier, g of x, is defined to be f of x minus the second derivative of f of x plus the fourth derivative of f of x, and so on, an alternating series of even derivatives of f of x. So g of x is this function. Little superscript 2k is representing an even derivative. So next, if we compute the second derivative of g, we get the second derivative of f minus the fourth derivative of f plus the sixth derivative of f, and so on. And then the clever observation is that if we were to add g double prime, or the second derivative of g, with the g itself, all that would be remaining is f of x. Now, why this is important is also not very clear at the moment, but we've established that g double prime plus g is equal to f of x. The next part is to observe the following: that the derivative of g prime times sine of x minus g times cosine of x is equal to, well, using the product rule, we can expand out what these derivatives look like, and we'll find that some of the terms in this expansion will cancel, and we're left with that the derivative of this expression, g prime sine of x minus g cosine of x, is equal to g double prime sine of x plus g sine of x. And we can factor a sine of x out of that, leaving us with g double prime plus g times the sine of x. And now what we established earlier becomes clear. This derivative is equal to f of x sine of x, which means we've just found an antiderivative when we take the integral. So integrating from 0 to pi on both sides of this equation well, that's going to allow us to evaluate this integral in terms of g and g prime. So we get that the integral is going to be g prime sine of x minus g cosine of x evaluated from 0 to pi. Observing that sine of pi and sine of 0 both evaluate to 0, this term will drop out. And because cosine of pi is -1 and cosine of 0 is 1, we're going to result in g of pi plus g of 0 is equal to this integral. Now again, it's not obvious why this is important, but what we established earlier through the binomial theorem and through the power rule for derivatives is that g of pi plus g of 0 is always an integer. The sum of two integers is always an integer. So that establishes that this integral is always going to be an integer. But to see this just a little bit further, consider g of pi. Plugging it into its formula, all the terms in let's say the even derivatives of f, with the factor a minus bx to the k power, will cancel to 0 at x equals pi, or a over b. Now this together with the binomial theorem really kind of drives home that this integral evaluated at pi and evaluated at 0 produce integers. So the similar argument is made at g of 0. This is a reasoning that's really concrete to showing how this proof is going to work, because we have now just shown that this integral must be equal to an integer, always an integer. Now we're going to tie it together now that we've established property number 1. Next, we're going to show that this particular integral is going to be greater than 0. So the function f of x on the interval from 0 to pi is always positive. And it's very easy to show that the sine of x, since the sine of x only takes on values between 0 and 1 in its absolute value, which I should have written there, on the interval from 0 to pi, and again, maybe the absolute value isn't needed on this interval, sine is going to be positive, and the product of two positive functions is also going to be positive, so we can make the argument that our integrand is always going to be greater than 0. Now, the absolute value of sine is less than or equal to 1, which makes the product of f of x and sine of x less than or equal to f of x. And since f of x is defined as this function, we can start creating an upper bound for f of x. On the interval from 0 to pi, we can write out the fact that f of x sine of x is less than pi to the nth power a to the nth power over n factorial. So now, if we integrate both sides of that inequality, we get that the integral from 0 to pi of f of x sine of x dx is less than pi to the n plus 1 power a to the n over n factorial. Now here's where we bring the contradiction to light here. By taking the limit as n goes to infinity, we're saying what happens as we let the value of n get larger and larger and larger. And what happens is that this ratio, this fraction, tends towards 0 because the factorial gets larger much quicker than the exponential pieces in the numerator. So for some n sufficiently large enough, this expression takes on values between 0 and 1. That is, it becomes a proper fraction. And if it becomes a proper fraction, and our integral is nested between 0 and an improper fraction, that means the integral itself has to be a number, a value, that is less than 1 but greater than 0. And therefore, this creates the contradiction. Again, let's spell it out. We showed that this integral here is always an integer. We also showed that this integral, for large values of n, is a number less than 1, a proper fraction, not an integer. Because of this contradiction, which is symbolized by two arrows pointing at each other, we have the following conclusion. The assumption that pi is the ratio of two integers, i.e. a rational number, is false. And therefore, pi is not rational. Or another way to say that is, pi is irrational. QED. I hope you enjoyed this proof. Please hit that like, subscribe, and notification bell for more videos. Stay tuned.